All right, so in our last class, we talked about the particles that were in the nucleus of an atom. And so this slide here is the last little bit that we'll say about the nucleus for now. We are talking about nuclear energy. In other words, energy that comes from the nucleus. So when you hear in the news things about nuclear weapons and nuclear bombs, the word nuclear is just referring to the nucleus of an atom, and that we can obtain energy from that. So here's basically how it works. Protons and neutrons, which I love to abbreviate with a P and an N, and when you're writing your notes, if you'd like a faster way to do things, that's a good way. Protons and neutrons are held together by really strong forces. That's why the nucleus stays all stuck together, all small in the middle of the atom, while the electrons can just willy-nilly wherever they feel like it. So there are really, really strong forces holding those two particles together to make up the nucleus of an atom. We also know that protons and neutrons are composed of smaller particles. So realistically, I could break them apart. I could also make protons and neutrons out of smaller pieces. So the idea is that even though those are the particles we discuss, we keep on discovering new things. And so maybe by the time you are as old as me, we'll have discovered something new about the atom that we didn't think existed before. Never say never with science. Now these two particles are what make up matter. And Einstein discovered that matter in the nucleus, so the protons and the neutrons, can change into energy. The idea is that if I can make something happen in the nucleus and disrupt those forces, I can get a bunch of energy from that. The way I would calculate that, which is not the goal of our course, I'm just telling you this so you know this is where it comes from, is the E equals mc squared formula. That's how we calculate how much energy matter can produce. The E is energy, the m is mass, the c is the speed of light. That's physics. You can take physics later in your life and learn to calculate things with it. I'm just letting you know that's how we would figure it out. There are a couple of reactions that I'd like to mention that happen in the nucleus. So they're called nuclear reactions. One of them is called fission, and the other one is called fusion. Fission and fusion release tremendous amounts of energy. And so just as a brief note, because the word fission and the word fusion are not exclusive to chemistry, we can use them in biology as well. And so knowing what those two words mean is relevant not only here, but in a lot of other topics as well. So before I just tell you what fission and fusion are, does anybody know what the difference between fission and fusion is? Or maybe you know what one of them is, but perhaps not the other. So I'm going to say a word that hopefully you heard at some point in Science 9 last year, Unit A, binary fission. It was a way that cells could reproduce and divide. Does anyone remember what binary fission is? I saw some people at least say, oh yeah, I heard that word. It's when a cell is dividing, and specifically binary fission, bi means two, so binary fission is when a cell copies all of its DNA and then divides in half. It's a way that cells can make copies of themselves. So fission is when you take one thing and separate it into two things. We could be talking about a cell dividing itself in half. We could be talking about a nucleus being broken apart, like we would be talking about here. But the idea is that fission means taking something and breaking it apart. Now fusion, and fusion can have a couple of meanings. Sometimes fusion is also used to talk about something melting, and we're not referring to that sense of the word here. So fusion is something that has more than one sense. Fusion in this sense is when we're talking about fusing two things together. Taking two things and making them become one. So I'm going to give you an example of a chemical fusion reaction so that you have an example like you would for binary fission, something that really happens that would explain this. Does anyone know what's happening inside of our sun? The sun that gives us light, heat, allows photosynthesis. Nobody knows what's happening inside the sun. There's a gas, it's reacting. Does anyone know which gas is inside the sun? It's number 1 on the periodic table. Starts with an H. Oh, it's hydrogen. There we go. So in the sun, there's a nuclear fusion reaction happening where atoms of hydrogen are reacting, undergoing this fusion. And long story short, hydrogen plus hydrogen, helium. I take 2 hydrogens, put them together, add up what I have. Looks like I have enough to make helium. When we say that our sun is going to burn out in whatever 4 point something billion years, what we really mean is that there won't be any hydrogen left for the sun to continue reacting. It will have all been converted through this nuclear fusion reaction and other things. So there will be no hydrogen left to burn. So the sun will no longer be a star the way that it is now. You won't be alive for that, so don't worry. It's your grandkids that'll have to worry about that. But that's an example of a fusion reaction. Does anybody have any questions about the nucleus and what happens there? So our goal today then is going to be to talk about electrons, which is the third of the subatomic particles. And they are the ones that are not in the nucleus. Does anybody need this screen to still be up because they're writing something off of it? So I'm just going to make this a little bit bigger. That's not good. There we go, page width. I guess that's as good as it gets, hey? So we're going to talk about electrons. I'm going to talk about what's written at the top and what's written on the side and then the picture. So don't think that you have to scroll this all down. Each thing will get discussed. Electrons are found in the nucleus. The word we usually use to describe where they are is orbit. They have a negative charge. That is why I often use an E with a negative to represent electrons. Now, when I talk about where they are, there's actually a couple of words that get used. In analogy, I would say that electrons are in like different levels on a shelf. We call them, but they don't refer to the same thing. So sketch here. If I was to draw it does not affect us. So back to what we were saying up here. To find the number of electrons in an atom, and this is really key, you just look at how many protons there are. If I'm not talking about an atom, what would I be talking about? I would be referring to something that has gained or lost electrons, and now I would be talking about an ion. Just so that we're clear, in an ion, the number of protons does not equal the number of electrons. I can't tell you for sure whether it would be bigger or smaller because it could be both depending on the situation. But what I can tell you is that they're not equal. And so if I ever gave you a question like one of the ones you'll have to do on the worksheet today, it's important that you recognize whether or not you have an atom, which is neutral, has no charge, it has the same number of positives and negatives, or do I have an ion, something that has a charge, something where positives and negatives are not equal to each other. So first, as a bit of a description, metal atoms. Those are things that are on the left of the periodic table. You might recall the other day we talked about how there's a staircase. Metals are on the left, non-metals are on the right, and that staircase is a nice thick black line that's on your periodic table in case you ever forget. It's quite noticeable. So metals are the things that are on the left. In chemical reactions, they will lose electrons. And the result will be positive ions. And the vocabulary word for a positive ion is a cation. Now, something that I used in the past to remind myself whether cation was positive or negative was to remember that a T kind of looks like a plus sign. You can use whatever you want to remind yourself, but that was my way. So metal ions lose electrons in chemical reactions to form positive ions. When something is a positive ion, it is called a cation. The reason it's positive is because since a metal atom lost electrons, they now have more protons than electrons. That's why there's a positive charge. So if I wanted to be specific, when a metal atom becomes an ion, the number of protons is greater than the number of electrons. If I'm talking about a nonmetal, which would be on the right side of the staircase, nonmetal atoms gain electrons in chemical reactions. They form negative ions, and the vocabulary word for a negative ion is an anion. I always thought this word kind of sounded like onion. Onions make people cry. That's bad. That's like being negative. And that was my trick to remembering these two things. Now that's the description of what an electron is and what happens when I gain or lose them. What we'll continue to talk about today and then again tomorrow is why. Why would something gain or lose electrons? What I'd like to show you first is visually what it looks like when something gains or loses electrons. So I have a little diagram here of sodium and chlorine. And what I think I might do is just re-sketch it, but a lot larger, because that one I know would be difficult to read from far away. So just give everybody a second. I'll check to see if anybody has any questions they would like to ask about electrons, ions, positives, negatives, that kind of stuff. Does anyone still need the screen to be up because they're writing something off of it? Okay, we'll just wait for a second. Looks like we're good over there. Is everybody good over here? Okay, I see one person still writing. Maybe I'll just tell you about one of my favorite chemistry cats. It's the one that says, I'm not trying to poison you. Now eat your PB and jelly sandwich. And it makes me laugh every time I think about it. And if you don't get it, look at what element PB is on the periodic table, because it's not peanut butter. Where's my thing? PB is lead. It's very funny. So the picture that I had on the screen that I'll just make a little bit larger was representing sodium and chlorine and what happens to those two atoms when they have a chemical reaction. So I will start with the sodium atom. In a sodium atom, we know from previous lessons that in the nucleus, I should be able to find a certain number of protons and a certain number of neutrons. Now, based on your periodic table, which you all have, sodium is number 11. So that means there have to be 11 protons. Since I've given you no other information, you could base your mass off of the periodic table. 22.99 is the mass of sodium. I would round that to 23. 23 minus 11, whoops, is 12. Let's make that a little easier to read. So there's my 11 protons and my 12 neutrons. That's what would be in the nucleus. Now, what really concerns us here are the electrons. A sodium atom should have 11 electrons because an atom always has an equal number of protons and electrons. So if I was to draw a sodium atom, I would start out by putting 2 electrons on the first energy level. That is the maximum for the first level. The second level can hold 8. So I would draw a second energy level with 8 electrons. Now, if I'm keeping a running total, that's 10 altogether. But there needs to be 11. So I would draw a third energy level with just 1 electron on it. That's what an atom of sodium would look like. Now, if I were to draw an atom of chlorine, I would use my periodic table, or I would remember from the daily review that chlorine is number 17. So it should have 17 electrons, and in the nucleus, 17 protons and 18 neutrons. It would have 18 neutrons because I would do mass minus number of protons, just like we did on the daily review. For chlorine's electrons, since I need 17 of them, I would put 2 on the first level, 8 on the second, and then on the third, I would put 7. Altogether, that makes 17. Notice how I always put electrons in pairs if I can. So that's why on that last level for chlorine, it's like I have 3 pairs of 2 and then 1 electron all by itself. The idea is that if these two atoms undergo a chemical reaction, this electron is going to transfer from sodium to chlorine. Now, if you look at the way the levels are set up, it kind of makes sense. Sodium has a third energy level with one lonely electron just sitting there all by itself. Chlorine seems to be missing one electron from its third energy level. If sodium gives that electron away, now they both have perfectly filled electron energy levels, and that's what atoms are aiming for. The result then is that we would have ions. I would have a sodium ion, and I would have a chloride ion. Notice that when I'm writing an ion, the first thing that changed was I put a charge. When I wrote the atom and its symbol, I didn't put a charge. When I write the ion, I have to. And that's something that you would be required to do on one of the questions on the worksheet. In a sodium ion, I would still have in the nucleus 11 protons, 12 neutrons. But I just gave away an electron. I only have 10 electrons now. So if I compare, I have 11 positive things and 10 negative things. The 10 negative things cancel out 10 of the positives, but that still leaves one positive left over. When I draw it, I would put 2 electrons in the first level and 8 in the second. Since I gave away 1 electron, the charge is 1 positive. I don't have to write the 1. I wrote it just now so you could see if there was a digit, that's where it would go. For the chloride ion, if I were to count, I now would have 18 electrons, but I would still, in the nucleus, have 17 protons and 18 neutrons. So since in this case I have 17 positives, they will cancel out 17 of the negatives, but there would still be 1 extra negative left over. If I were to draw it, 2 electrons on the first level, 8 electrons on the second, and 8 electrons on the third. So an ion has a charge when you write it, an atom does not. Now, if you happen to have pre-printed out notes, there's actually another slide, but I just explained what would have been on that slide. It was the idea of writing a symbol when you have a positive or a negative. And so this is where we're going to end today with notes.